Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today as it is every day here in my virtual classroom. Step on inside, enjoy some Monday Night Football, Jets and Bills as we do a 2.1 to 2.4 quiz on adding and subtracting polynomials, multiplying polynomials, special cases of polynomials, and solving polynomials by factoring using the greatest common factors only, not the other ones. Once we hit 2.5 to 2.8, I assume not only are we going to be doing bigger factoring, but I assume we get to also solve those ones by factoring in those ways. So more complex factoring to be had. Right now, only greatest common factors. Or they might, I haven't looked at the problems in great detail. They should be also maybe in factored form already. And we solve then using the zero product property. So that's a part of 2.4. We'll see when it shows up. I feel like I think it's only 1 through 21. This problem set hopefully isn't too heavy. Hopefully this video isn't too long. That should be pretty good. So if we can knock this one out, then all's good. Hopefully you feel pretty good about it as well if I explain it enough for you. If I don't explain it enough for you, you can ask some questions in the description section down below. In the comment section. In the description section down below, you can find a PDF of this 2.1 to 2.4 review in the Big Ideas Math Integrated Math 2 textbook, alongside the problem set and the timestamps down below for each particular problem. Okay, let's go ahead and move forward into these. Again, hopefully it's quick enough in that 1 through 21 and no graphs as far as I'm concerned. I think that'd be pretty cool. So we'll see how this looks. So for the first 4 problems, we're going to write the polynomial in standard form, identify the degree and leading coefficient of the polynomial, then classify the polynomial by the number of terms. I'll do you one better for the classifying polynomial. I will also classify, it says identify the degree. I'll identify the degree, but furthermore, I will classify the polynomial by its degree name as well on top of it, or at least that's my goal. So we'll see what the problems look like. So for number 1, we have negative 8q cubed. Now all of these by default are already polynomials because they're telling us they are, write it in standard form. Polynomials need to have variables with whole number exponents, 0, 1, 2, 3, 4, 5, everything onward. Can't be fractions, can't be negatives. They have to be positive integers or 0. And this one clearly is. It's a single term. It's a monomial. I just gave something away. But it's a single term polynomial. So standard form, there's nothing else to do. Here's the problem. I'll just put for standard form, we're going to have negative 8q cubed. Same answer. I can't do anything different from that. Identify the degree. The degree is 3. The exponent helps reveal what your degree is. The leading coefficient is the coefficient of the leading term when written in standard form. Here's standard form. The leading coefficient in this case is negative 8. It's the only coefficient that exists. And now let's classify it by name. Now, the name they want is by number of terms. One single term would make it a monomial. However, I also want to do it based on the degree. And a degree 3 polynomial is also known as a cubic. This is a cubic monomial. So number 1, there's the original expression. Obviously, standard form still the same thing, and we identify these things. And I know that, for now, it's probably uncertain as to how much degrees really matter and apply to what we're doing in leading coefficients. When you take IM2, they're going to matter greatly when it comes to graphing polynomials and talking about their complexity and such and dominance. So it matters. There's actually importance. The leading coefficient and the degree make a great deal as far as what your graph does. I'll just say that. Okay, number 2, 9 plus d squared minus 3d. Let's go ahead and write that out. And this time it has more than one term, so we can go ahead and get it in standard form afterward. So standard form is all based on the degree of each individual term. 9 has a degree of 0 because it is a constant term. It's almost as if this was 9d to the 0 power, like that. That degree is 0 as a constant. This is degree 2, the d squared, and this is of degree 1. When we write in standard form, we go in descending order of degree. So we start with the degree 2, d squared, and then degree 1, negative 3d, and degree 0, 9. It's basically expected that you do that every time, even when they don't ask for standard form. There are a lot of great principles to it that are helpful. Answer keys will show that. Always shoot for standard form no matter what you're doing. What comes next? Degree. The degree of the polynomial is 2. Now, there is something to be said, as I look at the other problems, it's not there. There is something to be said about a term with more than one variable. Let's say there was an e here. That's d to the first and times e to the first. You would add those two ones to get the degree of the original term to make that 2, or the individual term to make it 2. But we don't add the degrees for the polynomial. The degree of the polynomial is the degree of the leading term, and in standard form, that's 2. The leading coefficient is 1. 1d squared. That is the one that's there. The name of this polynomial. This is a quadratic. By degree 2, that makes it a quadratic. But by the number of terms, 3, that makes it a trinomial. Quadratic trinomial. Number 3. 2 thirds m to the 4th minus 5/6 m to the 6th. So the only thing for standard form, of course, that matters when writing in descending order of degree is the degree itself. Doesn't matter what these coefficients are. Keep that in mind. This is an m to the 6th, degree of 6. We're going to write that one first. And it's a negative. Negative 5/6 m to the 6th plus we got 2 thirds m to the 4th power. Just like that. Okay. So that's the beginning part. Now we go to the degree of the polynomial. Like I said, it's a degree 6 polynomial. Leading coefficient, that's going to be negative 5/6 for that one term. And the name, I don't know what a 6th degree one is. It's either sextic or let's see, I believe it's sextic. Degree 6, I'm searching this polynomial name. Sextic. So, I don't know if this passes some sort of sextic binomial. Or you can say degree 6, excuse me, 6th degree binomial. 2 terms makes it a binomial. 6th degree. I mean, I guess maybe this is a part of them not asking you to come up with that thing. Again, I hope that this bypasses whatever sort of a YouTube blocks that we have just by saying that. That's a math term, so that's all I'm going to say. But 6th degree binomial also works as well. I mean, I think they all have certain names going up to a certain amount. I'm sure for 58 they have one too. I don't know what it is. There's number 4. We have negative 1.3z plus 3z to the 4th. I'm having trouble writing. Plus 7.4z squared. I said this wouldn't take too long, but I'm only on number 4. They have a lot of things that they're asking you to do for each individual problem. Okay, so standard form. Degree 4 term starts first, 3z to the 4th. The next term is the degree 2 term, 7.4z squared. And then I have negative 1.3z. So those are standard form. The degree of the polynomial is 4. The leading coefficient is 3. And the name of this polynomial, a degree 4 polynomial is a quartic. That's different than quadratic, right? So a quartic, 3 terms once again makes it a trinomial. So we had quadratic trinomial and quartic trinomial. I know they ask you to name it just based on the number of terms, in which case say trinomial, but I'm also giving you those other words along the way. Hold on, I got some text popping up on my screen. Okay, we're going to go find the sum or difference numbers 5 through 8. So number 5, and by the way, they don't ask us to put it in standard form. I will always be putting these ones in standard form in the end. So 2x squared plus 5 plus negative x squared plus 4. So the version of what I'm going to do basically is rewrite this without parentheses and say how the parentheses or things outside of it affect the polynomials. In this case, they don't at all. When I add a negative, it stays as subtraction. When I add a positive, it stays as addition. So that's basically just what happens here. That's the rewrite. Now I'm going to combine like terms and keep it in standard form. X squared terms first. 2x squared minus x squared is x squared. And 5 plus 4 is 9. And you're left with x squared plus 9, which is also, like I said, standard form. And if you want to know the name, that's a quadratic binomial. Number 6. Number 6, we have subtraction. We have negative 3n squared plus n minus the quantity 2n squared minus 7. Now, the parentheses had no change or effect on number 5, and has no change or effect on the first quantity in number 6. That's still negative 3n squared plus n. But we're going to subtract this portion, which means you distribute the negative, or a negative 1 if you will, into these parts here. Negative 2n squared minus 2n squared, and subtracting negative 7 becomes a plus 7. Basically, those signs change when it's written without parentheses, and we look to combine like terms. Now, n squared terms still go first. Negative 3 minus 2 is negative 5, so I'm going to get negative 5n squared. I just have a plus n and a plus 7 afterward, where in standard form I get the linear term and the constant term written after that, and there's your result, at least in standard form. Okay, let's move on to number 7. Negative p squared plus 4p. Negative p squared plus 4p. Minus p squared minus 3p, the quantity p squared minus 3p plus 15. Okay. So once again, no effect on this individual quantity right here, but now when we subtract these, we basically change these signs. Minus positive p squared is exactly that, minus p squared. Minus negative 3p is a plus 3p, and then minus 15, like that. Negative p squared minus p squared, it's not 0, it's negative 2, and it looks like that's the leading set of terms, negative 2p squared. 4p plus 3p is 7p, and we have a negative 15 not combining with anything else, and there is the subtraction of those two polynomials. And then we have number 8, which is an addition 1, but it's a little bit different. Okay, so this one has multiple variables. It's a little bit different because it does have the multiple variables, so let's see what this looks like when we do a squared minus 3ab plus b squared plus negative a squared plus ab plus b squared. Okay, so I'm just going to once again rewrite it without parentheses. Maybe it might feel like a wasted step for some of you guys, but to notice, but to note what it would look like otherwise for subtraction, I think it's a very important step to just put in and to have one less cluster in the way. Anyway, adding the negative became subtraction there. This time I do have an a squared minus a squared, and that does become 0. A squared minus a squared is 0. I have a negative 3ab plus 1ab, which is negative 2ab, and b squared plus b squared is 2b squared. So that's my final result. Now, the interesting part, and I kind of wish the a squareds stayed in, because I might be boxing this and you might be saying, Mr. Robinson, you said you were going to do standard form. And I'll say I am doing standard form. This is standard form right now. So the reason I wish the a squareds were still there, let's imagine they were, and I have a 0 a squared, okay? This would have been standard form for this as well. And you're like, well, why? That's a squared, and this is degree 2, and a to the first and b to the first, 1 plus 1 is degree 2, and this is also degree 2. So these all have a degree of 2. So you might be wondering, well, then can you tell which one to put first and not? You can already kind of see it written the way that they have it written here. It's almost standard form-esque. All of these essentially were standard forms. That's one kind of giveaway with it. But also, and I've mentioned this in, I think, the other video when I did this at the time, you treat the alphabetically first variable as the dominant variable in your case. And when there's a tie, the tie goes to the alphabetically first variable more dominantly. This a is squared. This a is to the first power. This a is to the 0 power. There is no a there. So as far as a tie goes, treat it to the a's being of the higher degrees first, not the b's. So in this case, the 0a squared, it's not there, but this a is to the first power, and there's no a in this one, and that's why it is in standard form like that. Like I said, you can see it in the other problems. It kind of is represented that way. So that's my standard form, and like I said, it was kind of already expressed in standard form to begin with. Okay, we have numbers 9 through 14 where we're going to find and actually here, before I even talk about this, first of all, everything we just did before was in section 2.1. Secondly, looks like this is going to hit a little bit of 2.2 and 2.3 at the same time, what we're going to do. But what I want to mention is, as I write this problem out, w plus 6 times w plus 7, you know, excuse me, it probably should have been mentioned beforehand because we did the adding and subtracting. When you jump into section 2.2 and you're doing foiling, multiplication distribution, you actually probably feel pretty good while doing it. You're like, I understand this, Mr. Robinson. I'm doing good at it. You're going to do all that. That's fine. Just don't go back to 2.1, which I already just did. Don't go back to 2.1 and start going, I'm going to distribute these into here and multiply. You got to be very careful about what's in between. And I only bring this up because I've seen this a lot, where that minus or that plus is outright blatantly ignored. And the foiling, the distribution comes through multiplication. We're multiplying one quantity by another. And other cases, that's just not what we're doing here. So just keep that in mind. This is where multiplication comes into play. It wouldn't have happened before, but we can do it in this problem. Like number 9, we're going to FOIL. First terms, w times w gives you w squared. Outer terms, w times 7 gives you 7w. Inner terms, 6 times w gives you 6w. And last terms, 6 times 7 gives you 42. So that end result is w squared plus 13w plus 42. That's in standard form. That's the multiplication. And of course, there's addition afterward through that distribution. Or combining like terms, there was the distribution that got us there. And we're there. So again, that was the first outside, inside, last FOIL method. I'm going to stick to the FOIL method as long as I think it fits me. If there's a multi, like 3-term distribution thing, then maybe I'll look at it in a different way and use the table method. But I'm going to go with what will suit me best, what I feel will suit me best for these problems. Okay, let's go to number 10. Number 10, we have 3 minus 4d times 2d minus 5. So 3 minus 4d times 2d minus 5. Okay, so 3 times 2d is 6d. 3 times negative 5, outer, is negative 15. Negative 4d times 2d is negative 8d. Wait for it. Squared. Oh, how many people just put 8d? Especially after combining like terms. You just came from so many combining like terms things. I know a lot of you are going to just put the 8d. And then negative 4d minus 5, times negative 5 is positive 20. Now, I want to not only combine like terms, but I also want to get this thing in standard form. Am I missing anything here? 6d. Oh, sorry, 20d. Oops, see, now I forgot something. Okay, I want to combine like terms, but I also want to get this thing in standard form. Negative 8d squared is going to be the first term, and then 6d plus 20d gives you 26d, and then negative 15. Okay. That one becomes a little more clearly I messed something up. I'm so used to my last term being a constant that it's just force of habit there. So, I really like standard form, and this was not that, at least not to begin with. So it gets a little, hectic when it's not. Number 11, we have y plus 9. So this is a 2 by 3. This one might be good to use the table method and just show it. Y squared plus 2y minus 3. You gotta have two options here when it comes to multiplying. We don't FOIL anymore. It's not first, outer, inner, last, because you're gonna skip that 2y if so. But I will multiply y by these 3 terms, and I'll multiply 9 by these 3 terms. And that's that result that you end up adding some things over, and that's what we'd get. But for the sake of this problem, having a 2 by 3, a little bit more, I'm gonna go ahead and make this in the table format. And given that table format, what we do is we multiply this kind of like an area, like a base times height, where we take, y plus 9 can be this guy here. And then we're going to have that y squared plus 2y minus 3 as, say, the top, the base, the length, whatever you want to call it right here. And we're going to multiply these parts individually, and then we add together the result. So y times y squared is y cubed. Y times 2y is 2y squared. And y times negative 3 is negative 3y. 9 times y squared is 9y squared. 9 times 2y is 18y. And 9 times negative 3 is negative 27. So all these will add together. And again, that was y multiplying by all 3 of these and 9 multiplying by all 3 of these. That's basically the goal. And we add all these as a result of that. These two can combine. These two can combine. The rest of them, it looks like we just kind of get the result off of that. So we do have a y cubed as the leading term. Couple y squareds. 9 plus 2 is 11. Y squared, 18y minus 3y here, and the negative 27 in the end. So there's the table method. You can use it for a 2 by 2. I feel like that's more than is needed for those problems for the most part, but if they force it on you, you can do that. Here it says find the product, so there's no real requirement to do it one way or the other. Okay, number 12. Now, number 12 is something that you could go ahead and FOIL. We got 3z minus 5 times 3z plus 5. It's not only binomials that you can FOIL. Excuse me. I was saying you can FOIL it because they're binomials, but you don't have to do this by FOILing if you can recognize what kind of situation this is. This is known, and I forget how they say it in the book. I think it's a sum and difference product or something like that, where there's something that's subtracted and the same thing that's added in a way. Subtract the thing, add the thing. And that becomes a squared minus b squared. The result's known as a difference of two squares. where 3z minus 5 being the a minus b times 3z plus 5, a plus b, would also distribute into squaring 3z and then subtracting the square of 5, a squared minus b squared. Because what happens is the middle terms, positive 15z and negative 15z, cancel out. And then you're just left with these two multiplied together and the opposites of these two multiplied together. 3z quantity squared becomes 9z squared, square root of the 3, square the z, and 5 squared is 25, so you get 9z squared minus 25. Now I can go without writing this step, that's perfectly fair game, but just recognizing what it is for the sake of this review and this quiz is probably good to see here. Number 13 is another special case, and it looks like 14 is as well. These are part of section 2.3. Where, of course, you can do the foiling stuff, but this is even more important that you either recognize it for its special case or you expand this. It is not t squared plus 5 squared. You do not do anything of this sort at all whatsoever. Bar none, end of story, whatever, point blank, end of story, that kind of thing, right? You could do t plus 5 times t plus 5, and you can foil that out, right, in the same kind of way. But when you have a perfect, a squared binomial here, like a plus b quantity squared, that would actually expand into squaring the a, doubling the product of a and b, and then squaring the b. So a squared plus 2ab plus b squared, which would turn into t squared plus 2 times t times 5 plus 5 squared, like that. T squared is exactly that, it's t squared. Doubling 5t gives you 10t, and 5 squared is 25, and that's the result. It's like t squared plus 5 squared. I see my t squared and I see my 25, but you're totally missing this whole middle term. What does it matter? It means a great deal. It means everything, of course. It's a missing term. So, that's what happens when you multiply those. And then you have number 14, and I almost wanted to leave this one on the screen, so let me just copy and paste this over as I go to another page. But number 14, keeping this in mind, we have yet another perfect square trinomial scenario where we are going to be doing 2q minus 6 quantity squared. Now in this case, it's a minus b, and in the subtraction form, that means we subtract the linear term, but negative b times negative b is still positive b squared. It's still going to be the plus on that end. So this time, let's see if we can do this without kind of plugging those things in. I mean, I'm going to utilize this. We got to square 2q. 2q quantity squared is 4q squared. Now we are going to subtract this time. Minus, we are going to double 2q times 6. 2q times 6 is 12q, and we double that, and we get 24q. This is a lot of stuff that you end up doing in your head. You can end up doing in your head. I do in my head when I'm able to. Negative 6 quantity squared is positive 36. So that ends up being the perfect square trinomial bit expanded out from that. And it is good to note what these are. If I mentioned it in the 2.3 video at the time, this will help us when we hit section 2.7. 2.7 is all about factoring special cases. So knowing this scenario and what it goes back down into is actually pretty crucial to me. Okay, solve the equation. We have numbers 15 through 18, getting closer to the end. Now, solving the equations here, these are quadratic, so getting x by itself isn't quite as easy as it would be cracked up to be in other scenarios like linear equations, because I have two different terms that can combine. We don't try and move other terms over. We actually want to set this thing equal to 0. Our goal is to actually create a product out of this difference. These two numbers are subtracted, or these two terms are subtracted, but if we find a common factor of not just like 5 can divide out of both of these numbers, but also, more importantly, a variable, x. I can divide x out of x squared, and I can divide x out of x. And there'd still be something remaining inside of here, factoring being the opposite of distribution. You ask 5x times what gives you 5x squared? Well, that would be x. So you factored 5x out. You divided it out. It's just written on the outside. 5x times what is negative 15x? It's negative 3. So I rewrote this in factored form, and the goal of this was I've created a product. This is 5x times x minus 3. And when set equal to 0, you can use the 0 product property. If a times b equals 0, then either a equals 0 or b equals 0. Now, I explained this all in section 2.4, so you can go and take a look at that in the lecture portion if you'd like to. There's reason behind this. It only works for 0. That's why you need the set equals 0 and you need to create a product. 5x is essentially my a. 5x can either equal 0, or x minus 3, the other thing multiplying with that, can equal 0. You solve these separately. Divide both sides by 5, you get x equals 0. Add 3 to both sides, you get x equals 3. I can double check this. I can see that this works. You plug in 0. 5 times 0 squared is 5 times 0, which is 0. Minus 15 times 0, you get 0. 3. 5 times 3 squared. 3 squared is 49. 3 squared is 9. 5 times 9 is 45. Minus 15 times 3 is minus 45. 45 minus 45 is 0. Okay, that's number 15. Let's go to number 16. This is already factored. I have 8 minus g times 8 minus g equals 0. Now, we just came off distributing in section 2.3. It's actually counterproductive to start distributing and foiling this thing out. Factored form is what you want. You want the product. A times b equals 0. One of these has got to be 0. So either 8 minus g equals 0 or 8 minus g equals 0. I'll give you the heads up and spare you a little bit. It's the same thing twice. So whatever it is the first time, it is the second time. If I add g to both sides, I'm going to get 8 equals g or g equals 8. That ends up being the answer. Now, as the book mentions, they might separate into two. 8 minus g equals 0, 8 minus g equals 0, either g equals 8 or g equals 8. Now, I'm not saying it I'm not mocking the book. What I'm saying is that there's kind of redundancy to what's being stated. It's a repeated root. It matters for something. It actually does. But not for the solution set. G equals 8. It's the only value that can actually go into there. Number 17 is also in factored form. In number 17, I have 3 factors, however. We have 3p plus 7 and 3p minus 7. Looks like a difference of 2 squares scenario. And p plus 8. When you multiply those together, it equals 0. This still works as zero product property. This is an a times b times c. It doesn't matter how many numbers you multiply 0 with. It sucks it in like a black hole. 0 times this number times this number times this number times this number. It still equals 0 no matter what it is. So it just kind of takes it all away. So either 3p plus 7 equals 0 or 3p minus 7 equals 0 or p plus 8 equals 0. Now let's start with this one. You subtract 8 from both sides, p is negative 8, and you might have noticed that a lot of these answers have just been opposites of whatever you'd see inside here. Not always the case, because in this case, I'd have to add 7 to both sides and then divide by 3. I get p equals 7/3. An improper fraction like that is perfect. You want to leave it like that. Don't change it. That's the best answer you can get. Don't round it. Don't calculate it. Don't put a mixed number. You're all good. Subtract 7 and divide by 3. You get negative 7/3 here. Not going to double check on that, but there are 3 answers to this one. 3 different values for which you can get 0 for any one of these quantities, and when you multiply it, your product becomes 0. And then lastly, number 18, at least from this set here for solving the equation, we have negative 3y times 2 other factors, so negative 3y times y minus 8 times 2y plus 1. Now, this is one of those ones where maybe you could work a little bit more efficiently without too much work shown if you understand what's going on. Negative 3 is multiplying with y, multiplying with that, multiplying with that. If negative 3y equals 0, I mean, the only value that would work there is 0. Again, the negative 3 literally has no effect on this thing. Whereas y minus 8, the minus 8 does have an effect on this solution. Negative 3 is multiplying by my 0, by my root, by my thing that's going to get me my answer. It could be negative 13. Y still equals 0. Now, this other one, like I said, it just ends up being opposite of what you see here. If y minus 8 equals 0, y equals 8. You add 8 to both sides. Can you do this one in your head? If 2y plus 1 equals 0, I'm going to subtract 1 and divide by 2. Sorry, I guess I didn't really do it in my head. But I'll just write it out. If 2y plus 1 equals 0, you subtract 1. 2y is negative 1. And then you divide by 2. Y is negative 1/2. Okay. 3 more questions. Let's see how our time is. Half hour. Okay, pretty short. The shortest video of this series so far. Number 19. I'm not done. You are making a blanket with a fringe border of equal width on each side. Okay, so there's a little part where I want to maybe like draw it, but we got kind of like a rectangle. What do they call it? A quilt? A blanket. So you have something like that. They're showing that this width right here is like X inches. That's a 48 inches here and 72 inches here. So X inches all the way around. That's X, things like that. Right. Oh, geez. Hiccups. Hold on. Okay. Forgive me. Write a polynomial that represents the perimeter of the blanket, including the fringe. So these things are little X's right here. So the 48 is just the inner part. The outer part would add an X here and add an X here. So this whole guy would become 48 plus these two X's. I'd probably rather write 2X plus 48. This 72 also adds same X's around here. So that'd be 72 plus 2X around that. As far as perimeter goes, perimeter sounds more like section 2.1 than 2.2, but for part A, that would be 2 of the, I'm going to write 2x plus 48. 2 of the 2x plus 48s plus 2 of the 2x plus 72s. Because lengths and widths, you add all of those together. So that's going to be distributed 4x plus 96 plus 4x plus 144, which is 8x plus 240 inches all the way around for perimeter. I kind of ran out of room. I'll just do it, whatever. Forget the binder paper. Part B. Write a polynomial that represents the area of the blanket, including the fringe. So we're now going to multiply, it's length times width, base times height. We have 2x plus 48 times 2x plus 72. Might need a calculator for this one. Maybe I can try something without it. I can try something of old that we talked about in section 2.3 and try and go without a calculator. In some ways, I'm sure I could do 48 times 72, but I'll show you kind of what I'm going to do. It's kind of neat. All right, so 2x times 2x is 4x squared. 2x times 72 is 144x. 2x times 48 is 96x. And then 48 times 72, I'm going to figure out here in just a moment. But when I combine like terms, I have 4x squared plus 240x plus whatever this is going to be. Okay, how am I going to do 48 times 72? 48 and 72 are both 12 away from 60. This is 60 minus 12 times 60 plus 12. That's a difference of 2 squares. That is 60 squared, 3,600, minus 12 squared, 144. And 3,600 minus 144 is 3456. If I did that right. I believe. 3456, and that is that. Listen, I could have done the other kinds of multiplication, but I could have done that in my head. I wrote that out for you, not for me, right? So I could have done that in my head more than the other thing. And I'm not bragging. I'm saying someone else is like, oh, I did 72 times 48, and I did the thing. And I'm like, well, yeah, but I beat you. I beat you. Anyway, so there's the polynomial that is in squared inches when you come up with that area. Part C, find the perimeter and the area of the blanket, including the fringe, when the width of the fringe is 4 inches. So let's see. I'm breaking my whatchamacallit. I'm breaking my illusion here. I can't seem to expand that. That's okay. Okay, so part C. Find the perimeter and the area of the blanket, including the fringe, when the width of the fringe is 4 inches. So we have these two expressions that are also even combined together to help you. I'm going to substitute 4 for x. So for perimeter, let's do 8 times 4 plus 240. Basically, that's how much fringe is being added to the perimeter, all those bits. 32 plus 240 is 272 inches. And then for the area, a little more math to be involved. 4 times 4 squared plus 240 times 4 plus 3,456. I didn't even notice that said 3456. I don't know why. Anyway, I never trouble with multiplication. 4 squared is 16 times 4 is 64. It's addition that I have more trouble with than anything. So this is going to be 64 plus 240 times 4 is 960 plus 3, 4, 5, 6. This is the thing. I was like, don't make me do stuff. Good news, 64 plus 2, 4, 5, 6 seems a little clean. That's 3520 plus 960 is 4460. I think 4,460. Apologies if that's wrong. I think that's right. So 4,460 square inches, I believe. Sorry if I messed up a number there, but that math is happening. Okay, let's move on to another page there. Let's look at numbers 20 and 21, and that'll be it. Number 20, you are saving money to buy an electric guitar. You deposit $1,000 in an account that earns interest compounded annually. Is this a part of this section? The expression, squared. 1,000, let's see. I was like, this seems more like an IM3 thing, or chapter 1. The expression 1,000 times 1 plus r squared represents the balance after 2 years. That's why. Where r is the annual interest rate in decimal form. So A, write the polynomial in standard form that represents the balance of your account after 2 years. What they're asking you to do is expand this thing. They actually want you to do 1,000 times what 1 plus r squared will be. Now, I'm going to give you a heads up. 1 plus r squared is the same as r plus 1 squared. I think that helps me when it comes to my thought process, what I want to do. Standard form a little more so. R plus 1 quantity squared is a squared plus 2ab plus b squared. R squared plus 2 times 1r plus 1 squared, the perfect square trinomial expansion. That's expected of y'all when you do that. It's a section 2.3 thing. And distribute the 1,000, we get 1,000 r squared plus 2,000 r plus 1,000. That ends up being the balance of your account after 2 years. I'm not plugging in 2 for r. 2 is the time that goes up here. That's already applied to the problem. That's part A. Part B, the interest rate is 3%. What is the balance of your account after 2 years? So I do need a calculator for this, apparently. So the R value for 3% is 0.03. Now you have two options for this. We can either, I wonder if I can do that now. I need a calculator. You can either substitute it into here or into here. I personally kind of like the top one. That would be 1,000 times 1 plus 0.03 or 1.03 squared. If only I knew what 1.03 squared was. I could do, well, you know what? No calculator. No calculator. Here we go, guys. I'm going to start with what 103 squared is. How am I going to do that? I'm going to do 100 plus 3 squared, which is 100 squared plus doubling this product, 100 times 3, plus 3 squared. Boom. 10,609. So what is 1.03 squared? It's 1.0609. So boom, and like that. So this is going to be 1,000 times 1.0609. That's right, you can't beat me. So move this 4 decimal place. No, how many for 1,000? Move it 3 decimal places over there, and this will become 1060.9. This is money, so dollars and cents. Woo! I think I did that correctly without a calculator. At least that makes proper sense. It's 3% for only 2 years. So from 1,000 to 1,060, that seems appropriate as far as even the decimal goes. Part C. The guitar costs $1,100. Do you have enough money in your account after 3 years? Explain. Well, after 3 years, we would have to apply the same process but turn the 2 into a 3. So we would then have to do 1,000 times 1.03 quantity cubed. Or take this and multiply it by 1.03 one more time. Now 1.03 cubed, there's a way to do cubed format. I'm not going to get into that one in IM2, so I'm going to go ahead this time and actually use the calculator. 1,000 times 1.03 raised to the third power, and I'm getting 1092.727. Not approximate, it's exact. 1092 $1,092.727. $1,092.72 or 73 cents, whether it's one or the other, still not quite $1,100. No, I don't know how to explain. I guess their idea of explanation is show the calculation. But no, it's less than 1,100. But the idea is we had to substitute 3 instead of, we had to replace 2 with a 3, or do another multiplication of 1.03 in its place. I probably wouldn't have, well, we already had the number. I probably had no use for this polynomial anymore because we were now cubing. Okay, last question, number 21. The front of a storage bunker can be modeled by y equals, oh, one of these arch ones, can be modeled by, this is section 2.4, right? Y equals negative 5 over 216 times x minus 72 times x plus 72. Where x and y are measured in inches. The x-axis represents the ground. Find the width of the bunker at ground level. Well, tell you what, I forget if they gave us this much information before, but this is quite a bit of information that they gave us. I guess so. I guess that's what they gave us. But what we have, do I have a parabola tool here? I don't think I do. I don't think I have a parabola tool, so this isn't going to be a very good looking parabola. But you have what they call this, a bunker? But we have a bunker that kind of whatever looks like that. And we're trying to find this width from here to here. Now, the graph kind of reveals some of the things, but the end result is you want to recognize that the x-axis is where y equals 0. So if you set this equation equal to 0, and you solve for x, you find the x-intercepts, the values of x that I circled in blue. And those are, again, negative 5 over 216 has no bearing on what the x-intercepts are, just the graph in the tunnel. X equals 72 is one of your roots, and x equals negative 72 is the other root that you have. So this is at 72, 0, or 72 on x, and negative 72, 0 there. Now, what is the distance between these? 72 is 72 units away from 0. Negative 72 is 72 units away from 0. If we subtract their absolute value, 72 minus negative 72, we would get 144 as the distance. Inches. 144 inches. There. Okay, that's the width of the bunker at ground level, and that is it, and that is all, folks. That ought to do it for this one for the 2.1 to 2.4 quiz. Make sure you check out the PDF if you want to see some of the things for yourself. Write down these problems, and we move forward. After this one, and honestly, I'll just say this. I would have rather had a review from 2.1 to 2.3, and then one from 2.4 to 2.8. 2.4 with the factoring and zero product property is very connected with what's moving forward. So if you had trouble with it, keep practicing it because it's coming up in sections 2.5 to 2.8. That'll do it for this one, guys. This is Mr. Robinson. Thank you so much for watching, and I will see you in the next one. Take care.